Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today we're going to look at the second aspect of the concept of an ideal gas of diatomic molecules. And of course this is going to be a follow-up from the first discussion we had done on basically the concept of considering diatomic molecules in terms of rotational and vibrational partition functions. Now, of course, we said this one was going to give us a contrast between representations of diatomic molecules from the basic concepts that we have been dealing with on the statistical mechanics of atoms. In this case, I mentioned that basically for diatomic molecules, we're going to consider the rotational and vibrational partition functions. And the concept of rotational partition functions are mentioned basically that we are going to look at what we refer to as the degrees of freedom, whereby we said that diatomic molecules consist of what we call 3n, which is basically 6 degrees of what we refer to as freedoms. And of course, I mentioned that this degree is basically 3 for translation, and then I mentioned 2 for rotation, and then we had this is rotation. Let me write it correctly. So we had 2 for rotation and basically 1 for vibration in that specific order. So in this case, we said that considering this, we are going to take an example of a heteronuclear diatomic molecule, which basically we are given in terms of a rigid rotor that is going to be having this specific bond length, which is going to be considered to be fixed. And of course, I've mentioned that we can give an illustration of this specific diatomic molecule or heteronuclear diatomic molecule in terms of this particular distance, and of course the various components of their two specific masses given as such. And we had said that we are going to consider this specific aspect of the center of mass, which is going to give us an element of what we refer to as the moment of inertia by considering the radius between, or the radii between two specific centers of mass, the distance between the center of mass and these two specific position of the two atoms. And we came up with a specific representation for this specific element of the moments of inertia by finding it as a summation between I is equivalent to 1 to m for the sum of all the masses and then the square of the distance between them, whereby we have said that this R basically is going to represent the bond length. And of course, I had given a reduced or another illustration of this specific formula, considering the concept of reduced mass, whereby I said that this basically can be given in terms of this reduced mass and the square of that specific bond length. Now, in this case, I said that we can represent this aspect of reduced mass in terms of the product of the two masses for the two respective atoms of this diatomic heteronuclear diatomic molecule. And of course, this was the product of M1, M2, and then the sum of M1 plus M2 respectively. Now, in this case, of course, this first one gave us these two specific aspects that are going to determine what we refer to as the rotational properties of this specific molecule. And of course, we had mentioned that basically this constitutes the moments of inertia and the distance from the center of mass, which basically I've given in terms of these two radii for R1, R2 respectively. Now, this basically gives us a summary of what we had looked at, and I had considered the case that for us to find allowed rotational energies for this freely rotating molecule, then we're going to consider the Schrodinger's equation. And given this specific equation, Schrodinger's equation for determining this allowed rotational energy in terms of U, R, J, R for rotation, and then I had mentioned that this is going to be the product of this Bj and J plus 1 given as such. Now, I've given an elaboration for this specific formula, and of course we are going to discuss this one, or rather we have discussed this one. I'm going to put a link of that video in the description box concerning this specific aspect of B, which is basically a rotational constant. It's a rotational constant. And this, of course, is going to be discussing the theory of spectroscopic methods, whereby we're going to look at the rotational aspect. So this is a rotational constant, and then we're going to have this specific aspect of J. Now in this case, for considering this rotational constant, I'd say that we're going to assume this heteronuclear atomic molecule to be a rigid rotor with a fixed bond length. Therefore, this is going to be applicable in that specific respect. And we can have this J, which is a rotational quantum number, and rotational quantum number. This is quantum. This is a rotational quantum number, and we have specific values for the two specific representation for the rotational constant and the rotational quantum number in this specific order. So P is going to give us a value of the quantities which have got this specific ratio, which is the square of Planck's constant and 8 pi squared times the moment of inertia given as such. And of course, I've stated that a J, which is a rotational quantum number, is going to form a range of values from 0, 1, going in that specific order onwards. And then therefore, as I stated, of course, this specific, each rotational energy is going to have a specific state that we refer to as a degeneracy. And therefore, this degeneracy is going to be given in terms of, this is a degeneracy, and it's going to be given in terms of G. And therefore, this G is going to imply 2J plus 1 given as such. So these are various aspects of these specific diatomic molecules that we're going to consider from the particular illustration that I'll be given, and the various aspects which we're going to consider whenever describing this specific state of a diatomic molecule. Now, in this particular discussion, we're going to look at a way of expressing this, or writing an expression for the partition function for this specific kind of a molecule. And of course, we're going to consider various aspects like the rotational aspect, which I've mentioned in this particular case. Therefore, from the specific illustration that we had on the representation of this diatomic molecule, we're going to have a partition function which is going to also be represented using the concept of Q, which is equivalent to the summation of these individual energies for this negative BU rotation given as such. But before we proceed to this specific representation, I decided basically that the rotational energy diagram can be given for a diatomic molecule using this specific illustration, whereby we're going to have this one as increase in that rotational energy, and these ones are going to be respective values of G given in that specific order. So this is going to be G equivalent to 1, and G equivalent to 3, G equivalent to 4. So sorry for that. This is G equivalent to 5 and G equivalent to 7 respectively. Now, given a specific expression whereby we had G given, which is a degeneracy, of course, given in terms of G is equivalent to 2J plus 1. Now, if we try to consider this specific case, we're going to see that as the number rises, the values of B are going to be expressed in terms of 2B, and then we're going to have 6B, and then next we're going to have 12B given in that specific order. And this is going to give a rotational energy level for this specific diatomic molecule. And of course, if we do substitution, we're going to see that this is going to be increasing in that specific order. For instance, I said that if J is going to be assuming numbers of 0, 1, 2 onwards, if we have J equivalent, of course, to 0, or J equivalent to 0, then therefore we're going to have this specific representation for G given as 2, 0 plus 1, which is going to imply basically 1 in that specific case. But if we have J equivalent to 1, then therefore we're going to have, so this G is, if J is equivalent to 1, then we're going to have G given in terms of 1 plus 1, and this is going to imply 3 in that specific order. Then in this case, we're going to see that this specific impression, whenever G is equivalent to 3, is going to show this specific behavior, and whenever G is equivalent to 2, then therefore we're going to have 2 into 2 plus 1, and we're going to have this one represented as 5, and that's going to go in that specific order. So we can see that whenever this G is equivalent to this value for 2, then we're going to have this specific value for this G or whenever J is equivalent to 2, we're going to have this specific value for G given as 5, and this is going to be a state at this specific point given as such. And then whenever the value of G is equivalent to 3, then we're going to have 2 into 3 and plus 1, and this is going to be equivalent to 7 given in that specific order, and that's going to be going up that specific level. Therefore, we're going to consider the various representation for GB in order for us to interpret this specific rotational energy level given on my right. Therefore, we can proceed and look at a way in which we can give the partition functions of this specific aspect of partition function, and that's going to consider the rotational energy contribution as mentioned in this case. So we said that generally we can give this specific expression, which is going to be a sum of the specific energies and the number of degeneracies which we had given. So therefore, generally we have decided that I can give this specific representation for the partition function, considering this aspect of rotation in terms of the exponent of negative b, and then we're going to have this specific internal energy, which is considering the rotational contribution as such. And then therefore we're going to also now try to give this equation in terms of degeneracies, which I had mentioned, which is basically going to be a sum over the unique energies which are mentioned in this case, which is given in terms of the summation from I is equivalent to 1, and then we're going to consider non-degenerate states, and of course in this case we're going to have this specific range of degeneracy level from Gi, and then we're going to have the exponent of negative b, or we can just write this one in terms of over kbt, given in this is so this is going to be a general representation of this sum over the unique energies which has been multiplied by the number of degeneracies, or degeneracy of a number of degeneracy level given in terms of Gi. And of course in this sense, then therefore we can be able to represent the rotational partition function by combining the de Broglie's representation, which are given in terms of UJR, which basically give the allowed energies in our from our last discussion. Therefore we're going to have this one given as Bj J plus 1, and then I mentioned that basically this specific rotational constant implies 8 pi squared times the moment of inertia. So basically this is equivalent to that. Therefore we're going to combine these two specific aspects and come up with a general equation, considering the case of this particular degeneracy which we had just quoted in this particular case. Therefore, for me to have a rotational representation of the partition function, we're going to do a substitution and obtain this one in terms of the summation from the value of J is equivalent to 0, and of course this is going to go to infinity, and we're going to do a substitution for G, which is going to be 2J plus 1, and then we're going to have the exponent of the values of negative J into J plus 1, and then we have H squared given in terms. So we're going to use the concept of this specific Schrodinger's equation by doing a substitution for this specific value that we have given, and also considering this degeneracy that we have given in this first equation as such. So basically this last equation is going to be a version of this, but considering these two specific aspects of this particular value and this, and of course substituting for this degeneracy in terms of this. So this is going to be basically an expansion of it. The elements of 8 pi, the square of that, plus the moment of inertia is going to be an element of this rotational constant, and then we're going to have kb at t given in that specific case for this specific representation, and therefore that's going to form our equation given as such. So this is going to represent an equation, of course, which is going to represent the rotational partition function for this specific kind of arrangement, and that is going to be the rotational function of an ideal gas of a diatomic molecule. Now in our last case, I'm going to consider the aspect of perhaps what we refer to as a rotational temperature, and that's going to cater for a combination of specific elements which are going to cater for the temperature aspect in a Kelvin scale. So this is going to be last version of this specific representation. But in my last case, as I've said, I'm going to consider that specific aspect, and perhaps it's going to create a convenient way for us of representing this partition function. So catch us in our next video as we're going to look at that last aspect of that. And of course, it's going to give us another way of representing these partition functions of an ideal of a gas of a diatomic molecule. So that is it for now, guys. Bye, God bless you. Catch us in our next video.